Let's talk about the rank. What is rank? Maximum number of linearly independent row vectors in this matrix A. So I have a matrix. The rank is row vector. This is a row vector, row vector, row vector, row vector, row vector. How do we know that they are linearly independent row vectors? Yeah, so how do we check those row vectors are linearly independent? Suppose this is v1, v2, v3, v4, and v5. If those 5 rows are linearly independent, that means alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 plus alpha 4 v4 plus alpha 5 v5 is 0. And alpha 1 equals alpha 2, those coefficients are 0. Then they are linearly independent. If you find that v5 can be the linear combination of your v1, v2, v3, and v4, then v1 to v5, they are not linearly independent, because one vector can be expressed by the linear combination of other vectors. But if we cannot find any vector be the linear combination of any other vectors, then they are linearly independent. So in this case, for the matrix, I may have so many rows, and maybe those 3 are linearly independent. Then the rank A is just the maximum number of linearly independent row vectors in A. Then the rank is 3. If you find this is 5, the maximum number of linear independent row vectors are 5, then the rank is 5. Okay, so the rank will be less than or equal to the number of rows. It could be equal because, for example, this identity matrix, the row, these 3 row vectors are linearly independent, so they are 3. Then the rank is 3 because the maximum number here is 3. Okay? And we said that the rank A will be equal to the rank of the reduced matrix, because the reduced matrix, they are doing the elementary row operations. When they do row operations, it is just like doing the linear combination, right? This times 2 and add it to first row, or this just add to the 5th row, right? So it's like a 2v2 plus v1, or 5v2 plus v4. They are doing the linear combination. Okay, so the rank should be the same. So if it is really hard to find the rank of A, but if you can get the reduced matrix of A, then that'll be easier to check the rank, because this one, I don't know, the rank is 1, 2, 3, or even 0. But it's reduced matrix. I have 0 rows. I have 1 0 row. So this cannot be linearly independent. Then the rank A is 2, not 3. and this rank is also equal to the reduced matrix. Okay. Again, that, as I said, that for the linear algebra, for the topic 3, that you need to also think more in class. Hopefully that we are on the same page. Otherwise, you probably will be lost. Next, if the reduced matrix is an identity matrix n by n, then my rank is n. And of course, the A is an n by n matrix. Okay. Next, if you really take linear algebra, they will talk about the row space and also column space. Here, you just know what row space and column space, the definition, that's enough. I have A n by n. Then the row space of A, the matrix A is the subspace of Rm. N by m. And then they have linear combinations of all the row vectors. N by m. This is the matrix A. And the row space will be linear combination of those row vectors. Okay. The rank A is the dimension of its row space. So if you want to know the rank, you can either find the reduced matrix or find the dimension of your row space to see how many vectors you can make the linear combination. The elementary row operations do not affect the row space, okay, because you can see that this equation add 2 to the second equation, or this equation times 4 to the third equation. They are just doing the linear combination, right? V1, V2, V3, 2V1 plus V3. They'll become a new V3. V3 new. When they do the elementary row operations, it is like a linear combination. So they will not affect the space, the row space of a matrix. Well, just see this example. A matrix, I have A1 and A2. A1 is the first row. -1, 4, 0, 1, 6. A2 is the second row. -2, 8, 0, 2, 12. So the row space of the matrix A, all linear combinations of the row vectors. I have 2 row vectors, so there will be only C1 A1 plus C2 A2. I will consider all linear combinations of the row vectors. If I have 3 row vectors, then I will do the linear combinations of 3 vectors. But in this case, we can see obviously that the second row is 2 times of your first row. So the row space have all vectors alpha times -1 4 0 1 6. It is in R5 and the dimension is 1. And then the reduced matrix (1 minus 4 0 minus 1 minus 6 0 0 0 0 0). And the rank is 1. You see that the dimension is 1, rank is 1, because they should be the same. Okay? Once we talk about a row space of a matrix, you may ask then how about the column space? If we have a row space, then definitely we should have a column space. Now here's the column space of a matrix. We see everything in column rather than in row. So for the column, I can also have the linear combination of all column vectors. In this case, the matrix A is alpha 1 minus 1 minus 2 plus alpha 2 4 8, alpha 3 0 0, alpha 4 1 2, and alpha 5 6 12. All the linear combination of the column vectors that form the column space. And we say that -1 -2 form the basis and the dimension of the column space is 1. Because here you can see that it's like -2, you get 4 8, times -1 you get 1 2, times -2 you get 6 12, and times 0 you get 0 0. So they are not linearly independent. For this 5, not linearly independent. I can only get 1. I have this one, then I can express the second, third, fourth, and fifth one. So the dimension is 1. And here's a note. If A is a square matrix n by n, then the row and column space of this matrix will have the same dimension because it is square, like 4 by 4. You will also get the 4 elements in either row vector or column vector. After learning so many knowledges, finally, we're going to solve the equations. Here, we have the homogeneous system of a linear equations. Homogeneous means that here is 0. Okay, so I have n equations and m unknowns because we have x1, x2 to xm. And this system is called homogeneous because here is 0. Then how do we find the solution? All the solution. What is x1? What is x2? And also what is xm? First, we can write this system equation to the matrix form. Ax equals 0. If I can write it down as ax equals 0, this 0 is still a vector, right? Then what is a? And what is x and what is 0? So here I will have ax, x1 to xm equals all zeros. Okay, so instead of like writing so big matrix, I can use this expression having the element ij to show that this is the matrix A. And first I'll mark this is equation 1. So ax equals 0. I can do any elementary row operations, right? To plus, minus, or subtract, whatever. Then eventually we'll get the reduced matrix. So I will have, because those are still zeros, so I will have the reduced matrix times x equals 0. This is equation 2. Reduced system of equation 1. No matter it is ax equals 0 or the reduced matrix of A times x equals 0, they have the same solution. 1 and 2 have the same solution. And then why? Then since they have the same solution, which one is easier to find the solution? Of course, the second one, because the leading entries is 1, right? You don't need to multiply something. You can directly get the x equals what or y equals what. The second equation is easier to solve. Than the first equation. So row operations can be related to the operations on the equations of the system. As I just said that you add row 2 to row 1 and you times 3 of the row 2 to row m. Then they are still the equation, and it is just the linear combination of 2 vector rows or some vector rows. So instead of solving ax equals 0, now we want to solve the reduced matrix of ax equals 0. And how do we, then once we have the reduced matrix, then again, what is the solution of x? We need to find x. We will learn 3 methods or 4 methods. And those methods, each of these methods definitely will be in your exam next Wednesday. So you need to know how to solve ax equals 0 with different methods. First is called the Gauss-Jordan reduced method for this system, ax equals 0. So what is this method, Gauss-Jordan method? First, you need to find the reduced matrix. Then you can get the solution. Seek the solutions of a reduced matrix times x equals 0. Then the second, third, and fourth step, that's C. Second step, if column J of the reduced matrix contains the leading entry of any row, then if I have a leading entries of any row, then this xj is dependent. Otherwise, we will say x is independent. You see that column J, what does that column J means? This is row, right? Then here I have a column. column change, suppose this one, and I have a leading entry. Maybe leading entry is here. If I have a leading entries in that column, this corresponding x will be dependent. Otherwise, if we don't have the leading entries, like this one, I don't have a leading entries, this will be k, for example, then xk will be independent. Okay. Then solve, because I have a leading entries. I have a leading entry, then leading entries can be expressed to something, right? If I have a leading entries, this is xj, then xj should be equal to something. A or x equals 0. When we do the reduced matrix, then finally I have something here later on. So this is your xj. Leading entries will be your dependent variable. Solve the dependent unknowns as a sum of a constant times the independent unknowns. Independent unknowns will be, that means there will be x 5 will be 3x2 plus 5x7, for example. These are dependent, and these are independent. Dependent means I have leading entry. No leading entry. And for the independent unknowns, then I can assign any values later on. Okay. Let's just do one example that you'll know that what Gauss-Jordan method means. I think some of you probably learned that in your senior high school, right? Maybe the name is different, but once you see this, once you see the process, you probably, that can ring a bell. First step, I need to find a reduced matrix. So step 1. But to find a reduced matrix, first you need to know what the A is. Okay, in this case, what is A? This matrix A. Give me the first column. What's the number of first column? What is the element? 1 minus 2. Second column. Minus 3, 1. And how about the last column? 2 minus 3. Okay. Then you can find the reduced matrix. Be 1, 0, 0, 1, 7 over 5, minus 1 over 5. And here you can see that these two are the leading entries. You can also think that x1 will be minus 7 over 5 over x3. x2 will be like something over x3. So since I have a leading entry, that means x1 and x2 are dependent because they depend on x3. x3 is independent because we don't have leading entries for x3. Step 3. So we know that x1 plus 7 over 5 of x3 is 0. That means x1 is minus 7 over 5 x3. And x2 minus 1 over 5 times x3 is 0. Then x2 is 1/5 of x3. Next step. Then we can get the solution. The solution, x1 will be minus 7 over 5 x3 and 1 over 5 x3 and x3. This will be minus 7 over 5, 1 over 5, and 1 of x3. You can choose any number of x3. Say, we say that x3 is 5 alpha, since I don't want to see the fractions. Then the general solution. Is alpha minus 7, 1, 5. Okay. Any questions for this example? Let's see another example. Now I have 5 unknowns, x1 to x5. And if I can write this system to ax equals 0, what is the size of a? 1 by 1, 2 by 3, 4 by 5, 7 by 6. How much by how much? How many equations do we have? We have 3 equations, right? 1, 2, 3. Then row is 3. So the matrix is 3 by what? How many unknowns? 5. So it should be 3 by 5, right? 1, 2, 3, 4, 5. So let's write the A first. First, A is 1, 1, 0, minus 3, 2, 0, 1. And 3 minus, no, 1, 1 minus 3 minus 4, minus 7, 0, 0, and 4, 0, 1. Your homework, the reduced matrix, you should have 1, 0, 0, 0, 1, 0, 0, 0, 1, minus 35 over 16, 28 over 16, 7 over 16, 13 over 16, minus 20 over 16, minus 9 over 16. And you got leading entry, leading entry, leading entry. Okay, 3 leading entries and 2 independent variables. So x1, x2, and x3 are dependent. x4 and x5 are independent. When I say x1, x2, and x3 are dependent, that means these three variables depend on what? x4 and x5, right? You can see that x1 is equal to 35 over 16, x4 minus 13 over 6, x5. x1 is 35 over 16, x4 minus 13 over 16, x5. And x2 minus 28 over 16, x4 plus 20 over 16, x5. x3 minus 7 over 16, x4 plus 9 over 16, x5. Okay? Then we can express solution. The solution will be all from x1 to x5. I can express this as the linear combination of x4 and x5. So the solution is x1, x2, x3, x4, and x5. What is x1? Copy and paste. We have x4 and x5. Okay. Now we can choose x4 and x5. Choose x4 as 16 alpha, x5 is 16 beta. Then your general solution alpha 35 minus 28 minus 7, 16, 0, plus beta minus 13, 20, 9, and I don't have an x4, so 0, 16. So this, you can also write down this x4 plus something x5. Okay. Any questions for this one? How do we know that how many dependent variables or independent variables we have? Or even that when you see the equation, the system equations, how can I determine that their rank, their dimension? Or how can I predict how many independent or dependent solutions do we have? If A is m by m matrix, then the number of arbitrary constants in the general solution, arbitrary constants, that means I have independent solutions, right, or variable, because I need to choose that randomly but with a constant when they are independent. Then the number should be, because it is m by m, so that means you have m unknowns and m columns, so it should be m minus the rank of your A. If it is a full rank, then you don't have any independent variable. For example, if you have 3 by 3 matrix and your leading entries are also 3, then you don't have extra variables that are independent. So you can get a specific answer for x1, x2, and x3. And also the solution has the dimension m minus rank A. For example, this system equations, first the A is no x1, 0, 0, and then I have 2 and 6. 0, 0, 2, 6. Well, first, it's how much by how much for this matrix? I have 4 equations, 4 by how many unknowns? 4. This should be 4 by 4. Okay. Minus 0, 1, 0, 1, 2, 2, minus 1, 3, 0, 10, 4, 3, 7, 28. You will get the reduced matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 13, 10, minus 13, 0. First, you can check m minus rank. What is the rank? Actually, what is the rank of A? One, two, three, 4. Up to 4. You cannot say that 5, right? I only have 4 by 4. What is the rank of A? The maximum number of linear independent row vectors. This 3. Okay, so 4 minus 3 is 1. M is 4, right? The rank is 3. So since you know that m minus rank A is 1, then you should get and you should expect the general solution will contain one arbitrary constant. So the general solution is alpha 13, 10, minus 13, 1. Obviously, x1 is equal to minus 13, x4. x2 is minus 10, x2. x3 is 13, x4. And this is x4. Oh. So it should be minus 3. Okay. Any questions here? Actually, Ax equals 0. We always have a trivial solution. What is the trivial solution? Trivial solution. X is all 0, right? If x is all zeros, they always satisfy this equation. But how do we expect that we have a non-trivial solution? Suppose A is m by m. And then ax equals 0. We say it has a non-trivial solution. If and only if the n by m, you can always think it is the equations by the unknowns. So if the unknown is greater than the rank, so think about that, this is unknown. If unknown is greater than the rank, then definitely we have a non-trivial solution. Because the rank A should be less than or equal to the n. As I say, n is a number of equations. The number of equations will be less than the number of unknowns. Number of equations. And m is number of unknowns. So in that case, this system equation should look like, in this case, rather than the taller one, it should be like a flat one, because I have more unknowns. If I have like a taller one, that means I have so many equations, but I only have probably 2 unknowns. Then I shouldn't have. It's probably that I don't have solution, because there are so many constraints. That means x1 plus x2 equals 5. x1 minus x2 is 3. 2x plus 2y equals 4. 2x minus 2y is 3. Then probably you only satisfy is like the trivial solution, 0 and 0. So it is like a flat one. I have more unknowns than the number of equations. Okay. Now so far we just learned one method for solving the homogeneous system. And how about non-homogeneous system? If I have something in the forcing function, I have something else rather than all zeros. We can also use the same methods to find that. So consider a non-homogeneous linear system. Instead of 0, I have a b. You can think about the x and b, because we say the x is m by 1 matrix, b is m by 1 matrix. It could be also like x and b like a vector, because m by 1. M by 1. Oh, sorry. M by 1. I have m. And m by 1, that's just like a vector. So if I have instead of 0 vector, now I have one more column. Actually, I have one more column here. We can use the augmented matrix. What is the augmented matrix? I have my matrix A, but I also put one column for B here. And I use like a bar to separate that, to remind you that actually this is not part of your system A. Okay, so augmented matrix, I have a bar, and then I put the matrix B after. So here we have this bar, or sometimes you will see this is a dash. So this makes a dashed column. To remind you that the system is n by m. Because you need to know that how many independent variables and also dependent variables. For example, first, for this non-homogeneous system, just write down the augmented matrix. So for the augmented matrix, A, and then we have dash. B. So for A, 2, 1, minus 1, 3, 3 minus 1, and then separate that. And here B is 4 and 2, minus 2. Next example. So A and B. Two, 1, 4, minus 2, minus 1, 1. And then the B is 8, 1. Think about this one. Well, we think about that many times. 2x plus 3y plus 6z minus 6k equals 5. 3x minus 3y plus 7z plus 5k equals 10. I still can do the elementary row operations. This plus this, 5x minus 0y plus 13z minus k equals 15. Okay? Now, I'm still doing the elementary row operations, but for the matrix B, I also do the row elementary operations. Okay, so I can still find the reduced matrix of A, and then you can get the solution. So first, try to find the leading entry. This one, I can times minus 2 of the row 2 and then add it to row 1. Then I'll get 0, 8, minus 3, 1, minus 2, 1. And here I also do the row operations. 6, and here's 1. Now you can see 1 is here. I can switch 2 rows. It doesn't matter, right? Switch 2 rows, it just means that I switch 2 equations. So I switch 2 rows. One minus 2, 1, 0, 8, 3. Because I want to get my leading entries move downward to the right. Now the B is still 1, 6. And then I can times 1/8 to get the leading entry is 1. One minus 2, 1, 0, 1, minus 3 over 8. Here will be 3 over 4. 1. Now I need to remove or eliminate to make the element above and below the leading entry is all 0. So I will times 2. And then we will get 1, 0, 1/4, 0, 1, minus 3 over 8, 3 over 4. And this is your reduced matrix. Okay? Next one. I think next one, then we can just end up this class. I have 2, 4, minus 3, minus 6, 6, 18. And then you can do once you'll get so here you will see that 0x plus 0, 0x1 plus 0x2 equals 1. So I have no solution. So a non-homogeneous system may not have a solution. You can also check the rank. The rank A is 1. Rank A here only, okay? But the rank of augmented matrix, rank of A, B, this is 2. If we see this matrix as a whole, then the rank is 2, greater than 1, so greater than the rank of A, then we don't have a solution. So we say that if we don't have a solution, it is called inconsistent. And A and B, they have a solution. Ax equals B have a solution, and it is called consistent. To make sure that the non-homogeneous system has a solution, if and only if you see that the rank is different, then I don't have a solution. So if the rank should be the same, that means the matrix A and the augmented matrix has the same rank, 2, so have the same rank. All right. Then how do we find the solution? And now here I have a general solution. For this equation, remember that for the general solution, we should have a homogeneous solution plus the particular solution. So as you can see that H is a solution for the homogeneous system. And then U is the solution, we will say that for the particular solution. And overall, the general solution should be U plus H. Remember that for topic 1, in the beginning of this semester, how do I find the particular solution and how do I find the homogeneous solution? You need to separate these two systems and find the solution separately, right? And finally, you add them together. Then this time, let's see if we use the matrix form, the Jordan reduction method. How do we get the solution? So here we know the A, this matrix is -1, 0, 1, 1, 3, 2. Now I have a B, so I need to create an augmented matrix. So A with B. This augmented matrix will be -1, 0, 1, 1, 3, 2, and -2 and 4. Then you can find the reduced matrix. For the reduced matrix, or we will say both, the reduced one will be 1, 0, 0, 1, -1, 2, and 6, 4. Remember that for the leading entry, I need 1, and above and below there should be 0. And if I have 0 row, that will be at the end. And the leading entry is downward to the right. So in that case, we can check. First, we need to check if we have a solution or we don't have solution. So to check that if we don't have a solution, then we don't need to do the Jordan reduction method. So to check if we have the solution, we can see the rank. What is the rank A? Because we have the dashed line, so we know this is A and this is B. So for the A, what is the rank? 2, right? Then how about the rank of this augmented matrix? Still 2. Okay, so this is equal to the rank A, the augmented matrix B. What is rank? The maximum number of linear independent row vector. In linearly independent row vectors, if we have leading entries, then definitely these two vectors are linear independent, because I cannot use one of these vectors to express the other one, because here I have 1 and I don't have anything for that element. So they must be linearly independent. Okay. So if the rank is the same, then we can make sure that we have a solution. The system has a solution, and then we can try to find that. So since the rank is the same, the system has a solution. according to this reduced matrix, x1 minus x3 equals 6. x2 plus 2x3 equals 4. And remember that if I have a leading entry, those two variables are dependent variables. The rest will be the independent variable. So we can express x1 and x2 in terms of x3. Then your solution is the x. What is x1? x3 plus 6, x2 minus 2x3 plus 4, and x3. So we just let x3, a random scalar, say alpha, will be 1 minus 2, 1, plus 6, 4, 0. Okay. Then you can observe that this is my solution, and so alpha 1 minus 2, 1 is the general solution of the homogeneous system equation, and 640 is the particular solution. With the forcing term. So here you can see that through the Jordan reduction method, and we use the augmented matrix, then I can find the general solution, homogeneous solution, and particular solution at the same time. You don't need to separate, you don't need to find the solutions separately using just the Jordan reduction method. You can find both solutions together and get the final general solution. Okay? That means you don't have to find this equals 0. So you just try to find the solution for this A. And then later on you add 6, 4. No, you don't need to do that 2 times. Once you use augmented matrix, you do both at the same time. Okay. Any questions for this? See the next one. Okay, I want to know if we have a solution for this system or not. Okay. So to check if I have a solution or not, then we need to check the rank. Okay. What is the rank for matrix A, and also for the augmented matrix A and B? So again, that we need to write the augmented matrix first. 1 minus 4 minus 2 minus 1 1 minus 1 2 7 11 and 3 minus 5 14. Let me give you 5 minutes. Okay, try to find a reduced augmented matrix. So it should be 1, 0, 0, 0, 1, 0, minus 3, minus 5, 0. And the B here is 0, 0, 1. What is the rank for A? The maximum number of linearly independent row vectors. The rank A is 2. And how about the rank of the augmented matrix? Rank A B, there'll be 3 because I also have a 1 here. So the rank is not the same. This rank is bigger than the rank A, so the system has no solution. You can also see the third row, 0x1 plus 0x2 plus 0x3 equals 1. It's impossible, right? I cannot get any x1, x2, x3 to make this equation happen. So no solution. And because you also see that this is rank 3. But for matrix A, I only have rank 2. So they are not equal. So they cannot have a solution. All right. Next one. Wow. First is a routine work. Instead of just writing down A matrix, then we can just write the augmented matrix A and B. And this matrix is 1, 0, 1, 0, 1, minus 4, minus 1, 1, 3, 2, 3, 1, 1, 2, 0, 6, 4, 0. And then we have a B. 6, 4, 2, right? And then B is minus 3, 1, 0. Okay, and then you can find the reduced matrix. Here I give you the answer: 1, 0, 0, 0, 1, 0, 0, 0, 1. And the rest and here you can easily see that the rank A and the rank AB, the augmented matrix A and B, is the same, which is 3. right? So once the rank is the same, I can make sure that we can find the solution. And then for these leading entries, x1, x2, and x3, they are dependent variables, and we can express these dependent variables in terms of x4, 5, and 6. So x1 is minus 28 over 27 over 8 x4. And here's x2. Okay. So now I have x1 to x6. I can write down my solution x, that is x1, x2, x3, x4, x5, x6. So how about x4, there'll be alpha, x5 beta, x6 gamma, and IO times 8. 8 alpha, 8 beta, 8 gamma, so I can cancel the denominator. So I have minus 27, minus 13, minus 11, 8, 0, 0. For beta, minus 15, minus 9, minus 7, 0, 8, 0. Gamma, minus 60, minus 20, minus 12, 0, 0, 8. And finally, minus 7 over 8, 17 over 8, too big. Minus 17 over 8, 1 over 8, 7 over 8, and all zeros at the end. All right, so here's a note. I have a matrix A which is, n by n. Then AX equals B. This system has a unique solution. When, if, and only if the reduced matrix of A is an identity matrix of n by n. So if my matrix A is only the first 3, so you don't care about that, the reduced matrix is an identity matrix 3 by 3, then definitely I have a unique solution. x1 is exactly equals to minus 17 over 8. x2 will be 1/8, x3 7/8. Right. if I have identity matrix as my reduced matrix. But in this example, this is my reduced matrix. It is not the identity matrix because I still have something later on. So the solution cannot be unique. So that's why we have the parameters, the coefficients. If we don't have this, then we can say that x1, no other answer, just minus 17/8. So if the reduced matrix is an identity matrix. Okay.